Hello, thanks for coming to Modeling Bilevel Optimization Problems with BilevelJuMP.jl. My name is Joaquim Dias Garcia, and this is a joint work with Guilherme Bodan, my co-worker at PSR. This presentation is part of the JuMP Developer Seminar hosted together with JuliaCon2021. Now, a very fast intro or a crash course into bilevel optimization. Bilevel optimization was first developed in the game theory community by von Steckelberg, which defined what we call today as Steckelberg equilibrium, which is a game of two players where the leader optimizes its action by anticipating the follower optimal reaction to the leader's action. So these two players will be playing against one of each other, each one trying to optimize its own objective function. Although very flexible and useful kind of problem, there's no free lunch, and this class of program is NP-hard, as shown by Gerald's law in the 80s. The last step is a quick disclaimer, is that this package is stable but is under active development, so if some of the names and signature changes, beware. Now some applications and a little bit of motivation of bilevel optimization. Some classic applications of bilevel optimization have been employed in the operations research and management science community in the last decades. Two very interesting problems are the toll setting problem, in which an owner of roads or tolls will try to figure out the best costs of tolls so that it will optimize its own revenue, while the drivers, which will be the competing agent, will try to either avoid tolls or to use them if they are cheap enough. A second problem that was actually my first motivation for understanding bilevel optimization is the strategic bidding problem, in which a power system power agent or a power plant, something like that, will try to optimize its energy offer into a competitive market. A third class of problem that has gained a lot of attention recently due to machine learning is the hyperparameter optimization problem, in which we will try to figure out the best parameters so that we can get a good out-of-sample result. We will show an application for support vector machines at the end of this presentation. You can see many other applications in this interesting review by Stephen Damp. Here we show a general form of the bilevel optimization program. We will be following a general conic quadratic form from MathOpt interface, the lower level of JuMP. In this kind of problem, we will have a quadratic objective function, affine functions belonging to conic sets, and this defines the upper level program, which also has a second type of constraint, which will be another optimization problem by itself, which will be the lower level program, or the follower program, which also has a quadratic objective function and again an affine function belonging to a conic set. This is a very flexible form, and it's usually much more flexible than most of the works that use quadratic programs both in the upper and in the lower level. Now that we know what a bilevel optimization program is, let's talk a little bit about techniques to solve those kinds of programs. In the last decades, many solution techniques have been proposed, and here there is a short list with a few of them. Branch and bound is used to branch on the complementarity constraints, deciding either if a variable will be zero or if even a fine part of a function will be zero. Just like it would branch for MIPS-overs on integer variables or binary variables. The K-best algorithm, next, uses a lot of the techniques of the simplex method to look at dictionaries nearby a current solution and try to improve it locally. Genetic algorithms uses many classic techniques of genetic algorithms to solve bilevel optimization programs. The penalty method is based on ideas from interior point methods to penalize and with that obtain good solutions, local solutions usually for bilevel optimization programs. The cutting plane methods is a very promising method because it's able to solve programs with integer variables in the lower level, which are much more harder for many of the other techniques. Finally, we highlight the MPEC mathematical programs with equilibrium constraints, or KKT, Karushkon-Tucker reformulation, which is based on rewriting the program as a single level program, as we'll see next. Of course, there are many other kinds of reformulations that we're not commenting here. The MPEC reformulation, also known as the mathematical program with equilibrium constraints, is a method to rewrite the bilevel program into a single nonlinear optimization program. In this kind of program, we'll keep the upper level program untouched, so we'll just copy the objective function and the feasibility constraints of the upper level to this new program. Then we'll copy the lower level feasibility constraints to the program. To ensure the optimal solution will be attained by the lower level, we'll add the KKT conditions of this program, which include the lower dual feasibility, the lower stationarity, and the lower complementarity constraints. The first two, the lower dual feasibility and lower stationarity, can be obtained using Dualization.jl, while the last part of the program cannot be neither copied nor obtained with Dualization.jl. It will be written by BilevelJuMP reformulations that we'll see next. Here we present three classic ways of reformulating the complementarity constraints with mixed integer programming. So we'll take our complementarity constraint and either use an SOS of type 1, which will mean that either y, the dual variable, or f, representing the affine part of the linear constraint, will be 0, and the other one will be free to any value. Another type of formulation is using what is called the indicator constraints. In this formulation, f will be a binary variable, and if f is 0, the first constraint is enforced, and only that. While if f is 1, the second constraint will be enforced. This will guarantee that only one of these two will be valid at a time. The third one is known as the Fortuny-Amat or the Big M reformulation, which is very similar to the other two, but will have these big values of m, mp, and md, and this binary variable which will turn on and turn off one of the constraints in this disjunctive reformulation. Yet another way of dealing with the complementarity constraints is using nonlinear programming. So we reformulate the complementarity constraints as nonlinear program constraints. The first option is to remove completely the complementarity constraints and replace them by primal dual equality, which will enforce that the primal objective function of the lower level will be equal to the dual objective function of the lower level. And that's why we also say that this is the strong duality reformulation. A second option is to pass these constraints as complements itself, which some nonlinear programming solvers accept as information and will do automatically some reformulations on their own. The last option is almost copy and pasting the constraint, but that actually doesn't work due to numerical and theoretical issues. So people figure out that they can reformulate that with a regularizing term. So instead of forcing them to be 0, you just force them to be close to 0 for a small number t. And then you can try to reduce the value of t iteratively at each time. Each of the two groups of reformulation has its pros and cons. For instance, for the NLP, they are very fast to solve, very frequently. However, they usually attain local optimal solutions and might have trouble due to regularity conditions. On the other hand, the mixed integer formulations are very useful if you want to obtain global optimal solutions. However, they strongly depend on branch and bound, and hence, they might be very slow to be solved. And also, they might depend on hyperparameters like the big M's from the Fortuny-Amat formulation. Of course, these pros and cons are just rules of thumb, and depending on your program or formulation, each one of the two might be better or not. So this is BilevelJuMP.jl on GitHub. As you can see, we have already released version 0.4.2, and we've been still developing more new features, which are not on this branch, but are on the master branch, so you can check it out. And also, if you find it interesting, this presentation, remember to star us on GitHub so that we get more motivated to bring you more functionality. In this slide, we go through how to formulate a very simple bilevel optimization program in BilevelJuMP. As we can see, in this optimization program, we have an objective function on the upper level, a very simple objective function in the lower level, and then 4 polyhedral constraints in the lower level program. Well, the formulation in BilevelJuMP is very similar to JuMP. Instead of having the classic JuMP model, we have a bilevel model on which we can add variables to either the upper level or the lower level. So now we add x to the upper level and y to the lower level. The second step is to add an objective function. So we add an objective function to the upper level model, which will be a minimization objective function exactly the same as the LaTeX right over here is telling us. Then we can do the same thing with the lower level objective function, which could be a minimization or maximization, no issue. Finally, we can add all of the constraints of the lower level program. In this case, these 4 constraints are being added all at the same time. We could even add even more constraints, as we will see in a future example. Besides being very easy to formulate problems, BilevelJuMP has also some advanced features. We list 4 of them. First, it's the ability to get the dual variables from a constraint in the lower level and define them as explicit variables that can be used in the problem formulation. The second one is mixing formulations, so that if you have very good big M's for some Fortuny-Amat formulation, you can use Fortuny-Amat for that constraint, while if you don't have any good ideas of bounds for another constraint, you can use, for instance, the SOS reformulation for those constraints. That is especially useful in the case of conic optimization, where very few of the formulations are able to handle conic constraints, while all of the formulations can easily handle linear constraints. The third thing that is very interesting is the ability to pass additional information, like starting points that can be used by nonlinear solvers and bound hints that can be used to compute big M's in the Fortuny-Amat formulation. Last but not least is the ability to represent products of variables in mixed integer programming solvers. For that, we need to do binary expansions that can be done using an auxiliary package known as quadratic.binary.jl. Now we compare BilevelJuMP with a few other interfaces for bilevel optimization. We compare BilevelJuMP, BilevelOptimization.jl, which was a first version of bilevel optimization in the Julia language, based on JuMP also, PyYAML, which used to have a bilevel solver, which now lives in PAL, GAMS, which formulates bilevel optimization through EMP, Extended Mathematical Program, and YALMIP, that also has bilevel reformulations based on automatic dualization, whose feature for automatic dualization was actually a motivation for Dualization.jl. In terms of licenses, BilevelJuMP is very flexible because it's MIT license, which is as good as it gets. Also, BilevelJuMP is very interesting because it supports both MIP solvers and NLP solvers, which are both not supported by almost any other interface, except BiOmo, which supports both of them. But also, BilevelJuMP also supports MPEG solvers like Nitro and GAM solvers like Filter and MPEG, which of course are supported by GAMS by definition, and are supported in BilevelJuMP through the GAMS.jl package. Also, as we mentioned in the previous slide, BilevelJuMP can also model dual variables of the lower level explicitly in the problem, so you can use them during the modeling, just like GAMS could do in the past. In terms of the lower level formulation, we see that BilevelJuMP can formulate conic programs, which are not supported by the other ones, while BilevelOptimization.jl always require its lower levels to be formulated in matrix form. That's why it was the motivation for BilevelJuMP to implement for the first time algebraic modeling in Julia for bilevel optimization. BiOmo supports integer variables because it supports MIBs, a solver that allows you to solve problems with integer variables in the lower level. And GAMS uses EMP, the extended mathematical programming, so it's able to reformulate problems with the lower level, including nonlinear programs and variational inequalities. About the upper level, BilevelJuMP is together with BilevelOptimization.jl, which also relies on JuMP, and YALMIP having the most complete availability of resources, including conic programming, quadratic programming, nonlinear programming, and integer variables. This final example is especially interesting because it's very practical, very applied, and it's very clear to show off the powerful functionality of BilevelJuMP. So here we will model support vector regression hyperparameter tuning. So we have here in the lower level of the problem a classic support vector regression program where we are optimizing the support vector W, which will have this norm 2 penalization, plus the absolute value of the deviation of each of the points in the problem. So we have psi plus epsilon is greater than the difference between y and the estimation of y. We do both of the constraints to represent the absolute value. Here, c and epsilon are constants in the lower level, and they are being optimized by being properly chosen in the upper level. So c and epsilon are actually variables of the upper level model, which also has the psi variables, psi u, which are measuring how good or bad is the choice of w that we did in the lower level. With this structure, we are basically doing a correct, theoretically sound way of choosing C and epsilon, which could be done in practice by a grid search or so. But here we are formulating this as an actual bilevel optimization program that can be solved by some specific solvers. In this case, we're putting right on the right side over here the code for this same program. As we can see, the code is pretty much straightforward from the formulation. Just like we did before, we start adding variables to their correct levels, the upper and the lower level, and then we start adding the objective function of the upper level, all the constraints of the upper level, which are upper is right over here. We add all of the constraints. We can do that in a loop. We can do that multiple times for multiple constraints. And then we do the same thing for the lower level. We add the objective function and the constraints of the lower level, which completes the definition of this problem and allow us to solve this kind of problem with our solvers. In this slide, we show the results of solving the same model formulated by BilevelJuMP with different solvers and reformulation techniques. So in the first table, we have 5 solvers, CBC, Simplex, Gurobi, Skip, and Express, all of them using the SOS reformulation. And we have many instances, all of them for the support vector regression program. The first instance, 10-1, means that we have 10 observations and 1 feature, while the last instance has 1,000 observations and 5 features. In this table, for each solver, we show the objective function reported by the solver for the upper level program and the time or gap of the solution of the solver. If there is a time, it means that the gap was 0 at the end. If there is a gap in percent, it means that the solver took 600 seconds or 10 minutes and did not arrive to an optimal solution. In this other table next to it, we show the solution of the same program by IPOpt, Nitro, both using 2 kinds of formulations, the regularized product reformulation and the strong duality reformulation. As we can see, for the nonlinear solvers, we never see gaps because they do not provide optimality gaps, just the local solutions. However, we can see that they do report local solutions with very good quality. For instance, for the strong dual reformulation, both IPOpt and Nitro found in less than 1 second solutions that are very close to the best one obtained by CBC, which were not obtained by any of the other solvers. Moreover, we can see that the results of the nonlinear solvers are usually right above of the results of the mixed integer solvers, although the mixed integer solvers many times take much longer to solve the problems. Something that we have to keep in mind is that some of the nonlinear solvers might be reaching local solutions, so the objectives that they are reporting might not be actually the best solutions possible. Finally, some of our latest and greatest news. Currently, BilevelJuMP is part of Google's Summer of Code under the JuMP community. We have a student, Hesam, and 2 other mentors beside of me, and we are helping Hesam to build more docs and tutorials and to connect BilevelJuMP with the MIBS solver, which is very powerful because it's able to solve problems with integer variables in the lower level problem. Also, recently GAMS made available all its solvers in gams.jl package, which can be accessed from BilevelJuMP. So all the GAMS solvers are also available right now. And we have some upcoming news, which includes some new techniques that we've been implementing, including valid inequalities and more reformulations. So thanks everyone. That's all for today. And remember to just package.add BilevelJuMP and write and solve all the bilevel programs you can. See you there. Bye bye.